Okay, welcome everybody to CMSA Colloquium. It is our pleasure to have Professor Sheen from Harvard University. Professor Sheen received his PhD from Harvard University in 2006, and before joining Harvard University as a faculty member in physics department, he was a junior fellow at Harvard Society of Fellows and visitor member at the Institute for Advanced Study. And his research is in quantum field theory and string theory. And he actually received many awards, including to be a Sloan Research Fellowship and also New Horizon in Physics. Thank you. And today's talk is about introduction to Non-Perturbative Bootstrap.
Thank you very much for the introduction, for the elaborate introduction. I wasn't entirely sure what the audience was. My understanding was this was supposed to be kind of a broad audience, and I prepared a kind of very broad and elementary introduction to the subjects of non-perturbative bootstrap of quantum field theories. So much of talk, I would like to, much of it is that I want to share some opinion with you. If you like or not like, I like to say that in theoretical physics, most progress was made by making the right assumptions. So, if you're a mathematician, like to prove things, but I'm mostly going to be talking about what I think are the appropriate assumptions and the intuitions behind them. I think I probably don't need to explain the importance of quantum field theory, but I think some people, when they learn quantum field theory, or even after taking a course in quantum field theory, the idea of quantum field theory is computing, scattering amplitudes through Lyman diagrams, which is really kind of a tiny corner of the story because it's all about perturbation theory, and we understand very well now that perturbing quantum field theory only captures kind of the minuscule aspect of what the theory is. So the subject of I'd like to discuss is how we approach quantum field theory non-perturbatively. And in fact, non-perturbative definitions of quantum field theory have existed for a long time, for more than a half century right now. The problem is that there are many definitions, and they are not known to be equivalent. But nonetheless, these different definitions appear to be quite important, and I think as physicists, we're only sort of half a century later beginning to digest some of these definitions that have been kind of explored in the 60s. So I would kind of outline 6 different paths to non-perturbative quantum field theory. There are some things that most physicists like to talk about, such as path integral. So you might have to write some functional integration like this. In the usual sense, it's a functional integral. One has to define what we by the measure in the space of fields. And typically, this kind of path integral, in nice situations, can be made sense at the level of the Euclidean path integral, maybe discretized on some Euclidean space-time lattice. So we have sort of lattice field theory. Now, this is related to the Hamiltonian formulation of quantum field theory. Now, in order to define the Hamiltonian of quantum field theory in the correct way, once again, one typically has to do some kind of regularization or some kind of truncation. This is related to some of this is related to the so-called Hamiltonian truncation, or in some cases, a truncated conformal space approach, which will be yet another way to, in principle, to keep a non-perturbative formulation of certain classes of quantum field theories. The difficulty of either of these formulation is that it doesn't make all the symmetries manifest. But the symmetries or some desired properties manifest. Now, there's a closely related point of view is to focus on Euclidean correlation functions, or correlators, of local operators. The basic properties of Euclidean correlates of local operators was sometimes phrased as the Osterwalder-Schrader axioms. In this approach, one considers some local field operator dependent on space-time coordinate, and consider some Euclidean coordinate functions like so, where these xi's are parameterized some Euclidean space-time coordinates, and these coordinate functions are supposed to satisfy a certain set of properties. Some of them are kind of obvious. You need properties like Euclidean symmetry. You need things like cluster properties. That is to say that if you have a set of points, another set of points where you insert these operators and they're far away, then the coordinate function should factorize. Then there are things like reflection positivity, which has to do with ultimately relating this to the existence of some Hilbert space. I should emphasize that I think people who have not thought about this carefully often kind of underestimate the non-trivialness of the reflection positivity. For example, it doesn't just mean that, let's say you have a two-point function of phi x phi 0 for some scalar field phi. It doesn't just mean that this two-point function is positive. It means that two-point function is concave or convex. So it kind of looks like this. And that has some important implication, say, on the Fourier transform of this momentum space. And then there are these called temperedness, which is usually phrased in terms of the statement that if you integrate this against some test function in some well-defined distribution, for test functions that vanish sufficiently fast when the points collide, from my perspective, it's really a constraint on how singular the coordinate functions can get. As the points approach one another, typically you expect kind of singularity, but a singularity such that the coordinate function blows up polynomially, as opposed to e to the, say, something like e to the 1 over distance. That kind of singularity would not be allowed by the Osterwalder-Schrader axiom. Okay, so now heuristically, you're supposed to get to these Euclidean coordinate functions if you say start from the path table simply by inserting these fields into this functional integral. If you can actually do the functional integral, in most cases, in the theory of symmetry, we cannot actually evaluate the functional integration explicitly, and it's useful to postulate the existence and some properties of these Euclidean functions, first functions. So this is the third formulation. The fourth is the Weizmann axioms, or the Weizmann axiom, which concerns instead of Euclidean coordinate function, the Lorentzian coordinate function of let's say vacuum correlator between a set of fields 1 through phi xn, where this xi now are in Minkowskian spacetime. These two are related by analytic continuation. Often in many textbooks, especially physics textbooks, one is not very careful with what one actually means by this, and speak of this kind of relation as Wick rotation, which is a very sloppy way to talk about it. I will actually spend a few minutes later in the talk to discuss some aspects of this continuation, which is quite important. Related, so in this So when you speak of this analytically Lorentzian query function, now you can really think of these fields as operators acting on your Hilbert space. Although in order to make this more precise, you're supposed to actually integrate these Weidmann functions, which are usually physicists speak of these as query functions. They're really temporary distributions. You're supposed to integrate this against test functions of the Schwartz class, and then get some well-defined results. Using that, one can kind of associate with these local operators some actual well-defined bounded linear operators on the Hilbert space. For example, you could imagine taking phi to be some permission scalar field, and you write phi f to be something like integral, so some test function f of x, phi of x. So that would be some permission operator, but it's still not quite a bounded linear operator in general, but you can take something like e to the I phi f. This kind of way of thinking of trying to, instead of talking about these local operators with well-defined coordinate functions, one can instead talk about a set of actual well-defined bounded linear operators acting on your entire Hilbert space. This is related to sort of the algebraic quantum field theory approach based on a set of axioms that were proposed by Haag and Kessler. Basically, the rough relation between these objects are supposed to be that you can construct this actual well-defined bounded linear operator that acts on your Hilbert space by using these fields that kind of supported in some region of your space-time. So here I'm drawing some, let's say, take some set, open set U, and you consider its causal completion. To consider this in the causal diagram. I'm drawing this as a picture in the as a part of a Minkowskian space-time, and then there's some other kind of causal completion, some other open set V, and associated to this causal completion of this open set. There's some algebra of bounded linear operators that are supported in this region of your Minkowskian space-time. This is supposed to sit inside the space of bounded linear operators acting on your entire Hilbert space. And of course, then one impose some the Haag-Kessler axioms involves things like you have operators supported at space-time separate region. They're supposed to commute and so on and so forth. Now, the precise relation among these axioms are not known. It's not known whether to what extent they're equivalent. They're supposed to be morally equivalent, but there are a lot of subtleties. Now, this kind of approach to this way of thinking about quantum field theory, which has been around for a long time, has not really been appreciated by physicists until very recently, for the very strange, peculiar reason that somehow you can, in this formalism, where you have this local operator algebra, which is some von Neumann algebra, you can use it to define the so-called modular operator, which then can be used to construct some quantity known as the relative entropy. And somehow it kind of leads to a nice way to think about entropy of, or entanglement entropy of quantum field theory. That's kind of hard to approach in this point of view of local operators. Now, another thing that this Lorentzian query function is directly connected with is the S matrix. If you consider instead of these Weidmann functions, but time-ordered Lorentzian query function, if you time-order this and Fourier transform, and then it's expected that in the limit, when you take these momenta to be on shell associated to some, so the p squared would be approaching minus the mass squared, and for the mass of some stable particle, your theory, then this Weidmann function is supposed to, this Fourier transform time-ordered Lorentzian query function is supposed to pick out some pole with some normalization factor usually known as different names for this, I guess. I squared plus m squared times the S matrix element, S of P1 through Pn, where these momenta are now on shell with either time and energy correspond to incoming or outgoing particles, and this is supposed to capture the scatter amplitude of stable particles in the theory. It's expected that this S matrix will have some interesting analytic properties. I think I will, actually maybe I'll just discuss that a little bit now, just to illustrate why this way of thinking about quantum field theory is non-trivial. Of course, from the point of view of particle physics, this is why one was interested in quantum field theory in the first place, because we like to be able to compute scattering amplitude of particles. Well, the usual physicist way to think about the S matrix is that well, you have if you assume that your quantum field theory is such that if you have some stuff and you wait for a long time, the stuff interact and it will eventually decay into stable particles that will escape to infinity. Or if you evolve instead of into the future, if you time evolve into the far past, again, in the far past, you'll again find stable particles separated by large distances, and with the underlying assumption that these particles are supposed to be weakly interacting over long distances. If that's true, then you can define these in states, which are the states that look like separated, far separated particles in the far past, and these out states, which are supposed to be states that look like far separated particles in the far future, and their overlap is this S matrix. Is S matrix element. The S matrix element is supposed to typically have the structure of the sum of the products of the kinetic component of S matrix. For example, if you have a 3 to 2 scattering, you'll have some kinetic amplitude of 3 particles interacting together and decaying to 2. Then you can have 2 of them interacting into 1, and the 1 just kind of comes along with the ride, and so on and so forth. Now, each of these kinetic parts of the S matrix is supposed to be some delta function that imposes the momentum conservation times some amplitude, which is now going to be going to have some nice analytic property in the kinematic invariance spewed out of the momentum. As a non-trivial example, as a non-trivial example, if you think about the scattering, say, 2 particles into 2 particles, so you can write this as some delta function imposes momentum conservation for the kinetic part times some amplitude. I'll assume that these 2 particles are identical. This amplitude will be a function of the Mandelstam variables S and T, which represents the total, well, 2 particles coming in, or going out, so the total center mass energy squared is S, and momentum transfer squared is T. For example, now these things have some non-trivial analytic properties that can be argued on general grounds. So for example, if you consider identical scalar particles in 4 dimensions, then you can expand this amplitude in partial wave expansion that looks like something like this. So this working in units of the mass of particles set to 1. There's some formula for the partial wave expansion where L represents the total angular momentum of the system. So you have the scattering angle theta, which can be expressed in terms of T and S. These are the Legendre polynomials. And then you have this partial wave scattering amplitude, which is a number that characterizes the 2-to-2 scattering. But this number has, or a function of the center mass energy and the angular momentum of the system. Now, this function is sort of the partial wave scattering amplitude, which is the key player of the game here. And it has some kind of very non-trivial analytic property, just to illustrate the kind of things that would go on. So it's useful to, even though for a physical scattering process, the center mass energy is positive and S is center mass energy squared, which is supposed to be a real parameter. But it's understood that this object can be thought of as a limit of an analytic function along its branch cut on the S plane. So in my convention, if particle mass is 1, so branch cut starts from 4m squared, so 4 to infinity. It's not the branch cut, has to do with the T channel. So the physical amplitude is actually what you get by taking this analytic function on the complex S plane and approach this physical branch cut from above, let's say, in some convention. So the physical amplitude you get by taking such a limit. But it's important that there's the existent analytic function, and it's subject to some non-trivial constraints. For example, there has to be some stable particle that will get exchanged in this scattering process. Then you have some pole in the continue S into the uncritical regime. And it's believed that, in fact, all poles on the complex S plane have physical interpretation as intermediate on-shell particles. On the other hand, there's a two particle cut, and then there's some other cut that corresponds to some inelastic process. For example, if there are no other particles, it will start at 9, which is 3 times the mass squared. And we continue to below through this cut and to the second sheet, then you'll find that if you have some unstable particle resonances, you'll find it as poles on the second sheet, which is in fact the level of partial waves related to a 0 of this partial wave on the first sheet. So this partial wave amplitude captures a ton of the physics, essentially all of the physics of your theory. And symmetric bootstrap program is basically aimed at kind of constructing a set of complete consistent S-matrix elements that obey all the consistent condition that we believe should hold the S-matrix. Now, I just want to comment on why this kind of thing is non-trivial. In fact, not only this thing is non-trivial, in fact, we know so little about the non-perturbative S-matrix of quantum field theory that the only S-matrix that I'm aware of that's can be determined exactly in any quantum field theory that's not a free theory are 2D integrable models. And those models are no particle production. So the situation is a little bit similar to, if you contrast this situation to non-relativistic quantum mechanics. So in non-relativistic quantum mechanics, you can also talk about S-matrix scattering, and often one can write exact analytic formula. And the reason it was easy in that situation versus in general quantum field theory is that there's no particle production or in non-relativistic quantum mechanics. And it's much of the complication about the S-matrix quantum field theory has to do with particle production. And in fact, it's hard to write down any consistent S-matrix at all if you have particle production, and that's which is partially why it's kind of a non-trivial and kind of a potentially fruitful approach. Now, I should also comment on that. It's often said kind of colloquially that the S-matrix bootstrap program has been around for a long time, and somehow people got stuck. In my opinion, people never really got stuck on the S-matrix bootstrap program. People just got distracted by the temporary success of perturbative quantum field theory. And in fact, now I think many people are kind of revisiting some of the old ideas, really with not that much new input, but just the fact that there's actually a lot of good stuff in this old approach to S-symmetry that has not really been explored to the extent that they should have been.
Actually, just to be clear, I mean, the partial wave statement up to this point was sort of known in 1958. What got people excited was Mandelsam's appearance on the scene that started talking about the analyticity in S and T at the same time, and not just in S in the partial wave expansion, it's function of cos theta. You can go a long way just talking about this, but you're not using very much about relativity in this construction.
That's equivalent to crossing symmetry, right? So
that's true. You're adding crossing. You're adding crossing, which allows the branch cuts.
That's all about crossing. So
right.
you know, at least a part of it. It's just the question of how do you control the behavior along this other cut.
True,
because,
but if you allowed, I'm just saying, you can have non-relativistic quantum mechanical systems with particle production, and apart from crossing, the analytic structure is exactly the same. It just sort of follows from quantum mechanics, from unitarity in quantum mechanics, part of the reason people tried to go more than that is that they really wanted to somehow determine the whole thing. And so there, they thought they would get more information on analyticity in S and T, and that's the thing which is still a morass that we don't understand. Well, we don't understand ahead of time.
I would say that just think about analyticity in S and not in the crossing. It's already a tremendous amount of constraint, and we're not even close in exploring just consequences.
I agree with that. I agree with that. But I'm just saying because people in the 60s, in a sense, that their ambition was to totally uniquely derive theory, which is wrong, we understand, but still, they got excited by the fact that there was more analyticity than meets the eye. And then they thought that it would continue to be true with S and T, that all the singularities were physical and could be interpreted. That's what's wrong. It's not true that all the singularities in S and T all have physical interpretations in Minkowski space as ordinary physical processes. There's the infamous anomalous thresholds and worse.
But the anomalous threshold was also understood around that time, and so that's many textbooks. There's complete understanding of all the Landau singularities. So
there is no complete understanding of all the Landau singularities, and in fact, people don't know what to do when there's anomalous thresholds. That's a problem. That's why they're anomalous. So you can treat them case by case, but it's exactly. Anyway, this is besides the point. I just wanted to make
No, but are you saying the Landau equation should not capture all the anomalous thresholds?
Well, they capture it, but first, the Landau equations have complicated solutions. They have not been
of course. I mean, they're complicated. That's
Secondly, the problem is just because you know where because of where the branch, where the singularities are, does not mean you know how to control them. That's the problem. When the singularities occur in Minkowski space, they have a physical interpretation in terms of unitarity. The difficulty, the word anomalous, is that those do not correspond to processes that take place in Minkowski space, and so you don't know what to do. The whole philosophy breaks down because you don't know how to interpret the discontinuity across those branch points, and that's why you have to start being more adventurous. So they started thinking about interpreting them as processes into two-signature or equivalent. They didn't say it that way. Or analytically continuing results you got, into the place where it's anomalous and so on. But the whole other game began. That's all I'm trying to say. Is that what the sort of abstraction to the S matrix program was not at the level you're talking about, which is perfectly beautiful, and we know the analytic properties just from quantum mechanics, but was in trying to lift it to something that said something about analyticity in S and T at the same time.
I would say that even in a situation without an anomalous threshold, the scattering line is particle to scattering, even that had not been fully explored.
I entirely agree.
It's hard to even write down any example of that.
I'm not disagreeing with you. I'm not disagreeing with you. Yeah.
Okay, so anyway, this is what the S-matrix bootstrap is about. In fact, but I will not get into it further in this talk. In fact, I guess in this workshop in December, I'll actually give a talk about some recent work on the two-dimensional S-matrix in what I would consider the simplest non-trivial quantum field theory that's not integrable. So I want to now discuss a bit about the property of Euclidean Fourier functions, which is kind of the central object of the conformal bootstrap. And in fact, in some sense, the kind of the philosophy of the conformal bootstrap, let's say in comparison to this kind of algebraic quantum field theory approach, is almost the opposite. Because here one like to think about all the operators of the theory at the same time, but in the bootstrap, we like to focus on one or a very small subset of operators. Now, you might think that by doing so, you are kind of restricting yourself to a tiny corner of theory. You have no chance of getting the full picture. But that's in fact not true. Typically, for example, if you just take a single scalar field in some generic single scalar field in some quantum field theory, and consider the operator product expansion. So if you insert these two operators in some place in Euclidean space, you will produce a state that lives on, let's say, a sphere that surrounds some domain that contains those two points. Essentially, up to some caveat, essentially almost any state of your quantum field theory that can possibly live on that sphere that's not forbidden by some symmetry, some conservation law, will generically appear in the operator product of a pair of identical scalar field. In fact, if you can determine exactly the covariant function of just 4 scalar fields in some quantum field theory, then you know a tremendous amount of information about the theory. In fact, you know essentially most of the states in your quantum field theory that are kind of neutral with Ragusson global charge. Let's say if you have a situation where there's no global symmetry, then such a 4-point function should essentially capture almost all states of your theory. Of course, in fact, this generic 4-point function of some scalar field in quantum field theory is a tremendously complicated object and contains a huge amount of physics, but there are rarely any situation where you can write a closed form formula of the 4-point function. I think much of the rest of this talk, I'll just discuss properties of 4-point function of some scalar field in quantum field theory. And for the reason discussed here, I'll just focus on the Euclidean situation where it's simplest to think about the analytic property. By the way, I should say that in the literature, it's sometimes stated that this kind of the set of Euclidean axioms, which are the Osterwalder-Schroeder axioms, and then there's a set of Lorentzian-Weizmann axioms that's supposed to be equivalent when you do that configuration. But the ground on which these things are equivalent was supposed to be provided by the Osterwalder-Schroeder reconstruction theorem. But most of the assumptions of the reconstruction theorem are standards, and you can actually, in some examples, it's easy to understand why they should hold. But then there was a extra axiom, which is some growth condition about n-point functions, how it grows with n. It cannot grow faster than basically some power of n factorial. And this growth condition is somewhat mysterious. That was apparently needed to prove the equivalence, and that condition is very hard to check. So because of that, the general actual equivalence between this Corday formulation and the Lorentzian formulation is not on a, I would say, a completely rigorous footing, as far as I know. Okay, but anyway, let me for now talk about this 4-point function. And I'm going to simplify my life by referring to quantum field theories that are conformally invariant. So why conformal symmetry? So we expect that the low quantum field theory should contain a special operator called the stress energy tensor to mu of x that's symmetric and conserved. It's well-defined local operator. The well-defined current functions of the stress energy tensor. It's a symmetric tensor, but with back to the Poincare group or the Euclidean group, or let's say the rotation group. Of course, you can decompose this into its symmetric traceless part, and then the trace part. The trace part itself is some, you can call it O, is itself some scalar operator. And one could imagine that depending on how this operator behaves in the limit when you scale to large distances or scale to short distances, the effect of this operator goes away, and then you end up with a theory in which the trace of the stress tensor is 0. So this is the one way to define a conformal field theory. If the trace of stress tensor is 0, then it leads to a set of a new set of conservation laws. You can write down actual Noether currents, and in the Euclidean signature, the Poincare symmetry is enhanced to the conformal symmetry, parameterized by the group SOD plus 1,1 for d-dimensional space-time. The simple way to explain the conformal symmetry is that it's just generated by the Poincare symmetry. The dilatation, which act on the coordinates as sending scaling of the coordinates, and a inversion symmetry. There's a slight caveat to this. I'm assuming parity varies, but we don't worry about this. So we send x mu to x mu over x squared. And these together generate this. Of course, it's a discrete transformation, but these together generate the entire conformal. Okay, so let me assume now that assume this our scalar field phi transforms under dilatation and inversion in some nice way. One can argue that on general grounds that all operators in a unitary conformal field theory can be written as linear combinations of operators with such nice properties and their derivatives. So we'll assume that I transform in the following way. So under dilatation, where you rescale x mu by lambda x mu, phi of x transform into some phi prime of x, such that phi prime at x prime is equal to lambda to the minus delta phi phi of x, where this delta phi is a number of the scaling dimension of the conformal weight of the operator. And under inversion, phi of x transform into some phi, I call it phi check of x, where I guess I can call this x check mu. So phi check evaluated at x check is equal to x squared power delta phi phi of x. And of course, under Poincare symmetry, it transforms into the standard way as a scalar operator, the local scalar operator. Now, using these conformal symmetries, you can sort of map generic 4 points in Euclidean space to the following special configuration. So we can use the d plus 1, symmetry to put the xi, these 4 points, so x1 through x4, in a plane inside the d-dimensional Euclidean space. And without loss of generality, I can assume that this, let me parameterize this plane as the complex plane, and the 4 points will be 0, 1, infinity, and some other point, generic point z. So z is complex coordinate. Then, using this transformation rule I wrote here, one can always express this in terms of the 4-point function when we move the fields to 0, z, 1, and infinity. This is, you have to do some suitable scaling to make this finite and well defined. This will be some function of this complex parameter z, and so far it's z bar is which is its complex conjugate. So this is the central object of interest. It's really, so in the conformal field theory, the non-trivial data of this 4-point function is really captured by a single function of one complex variable. So that sounds pretty simple already, but the whole point is that this one function of one complex variable is, in general, conformal field theory, some incredibly complicated object and has tremendously rich properties, some of which I will now describe. This is the kind of, it's the central object in this whole game of the bootstrap. Okay. So, I'll just say ahead of time that is what I've learned that is very important and very, very useful to consider the analytic continuation of CNC bar independently. In fact, as I mentioned earlier, that condition will lead to Lorentzian Fourier functions. So, indeed, if you analytically continue CNC bar independently, you can relate this Euclidean Fourier function to Lorentzian Fourier function with some expected properties, which I'll comment on in a bit. But first, let me just say a few words about this Euclidean Fourier function. It's expected to be a real analytic function of CNC bar, as function of the real and imaginary part of Z is supposed to be analytic on the real analytic sort of away from what did I say? R2 minus 0 and 1. So typically you expect some singularity when the two local operators collide. So you have some singularity when Z approach 0, Z approach 1, and Z approach infinity. And that is supposed to be depend analytically on the Euclidean coordinate. Now, a important constraint of the conformal symmetry, together with locality, is that not only this 4-point function obeys conformal symmetry, but the state you get by taking the operator product, the two of the phi's, which produce a state on this sphere, is supposed to produce this state, schematic call it phi. The state is supposed to transform, belong to some Hilbert space that transform under the conformal group. And in particular, one can, so the Hilbert space of state living on the sphere will, d minus 1 dimensional sphere, will comprise of the direct sum of various representations of the conformal group. And in fact, the state can be decomposed into irreps of the conformal group. So b plus 1, 1. But in fact, there will be unitary representations of the Lorentzian version of this, which is SO b, 2. Essentially by the conformal transformation that relates the RD to this cylinder, which is R times the sphere. Now, in the situation, in the simple case where I consider the OPE of a pair of scalar operators, the possible representation that can appear are restricted. They're not the most general possible irrep. The general irrep will be labeled by some dimension, scaling dimension delta, of the state that appears in this operator product, together with some representation label of the rotation group of the sphere as b minus 1. In the situation of the operator product of a pair of scalar operators, it turns out that the only such irreps that can appear in this operator product will involve symmetric traceless representation of the SOD rotation of rank, let's say L, which is of course a non-negative integer. We usually refer to this rank of the symmetric traceless representation as the spin of that operator that appears in the operator product. So that is to say, if you take this state produced by taking the product of a pair of scalar operators.
You think they're identical?
They're identical. They're identical. Then everything in this operator product can be expressed as some operator of dimension delta, some spin L, and their derivatives. Okay. So this allows you to kind of decompose this 4-point function, which I've now expressed as f z and z bar, as a sum over all the possible representations that can appear in this operator product. And as I said, this representation is labeled as dimension delta and this integer L, which is the spin. In this case, with some coefficients. This coefficient, it has an interpretation of some kind of inner product, so it will be some positive quantity. I'll write it schematically as some coefficient A delta L squared. Right. A is a real number, just to indicate that this quantity is positive. And then there's some universal function that appears here, which I'll write for convenience as after some universal factor. I'll write this function as g of z and z bar. It depends on the representation that appears in this operator product, and it depends on the dimension of phi itself. But apart from that is a universal function. It's known as the conformal form. Now, in fact, there's a nice way to determine what the conformal block is. It's in fact a solution to a second-order differential equation. That is the equation that says that the conformal block, the function of this z and z bar, is in fact a eigenfunction of the conformal Casimir. So you can write some differential operator, second-order differential operator called L squared. That is so the Casimir operator of this so d comma 2, this conformal group. You can realize these operators as differential operators acting on this 4-point function, and this conformal block, which corresponds to some irreducible representation, will have a well-defined eigenvalue with respect to this Casimir operator, which is some differential operator. I won't write the explicit expression. So it basically looks like this, where this c is some number that's determined by the way it's the Casimir of that representation. Now, this differential equation doesn't have a unique solution, but you can fix the unique solution by studying the limit, say z bar going to 0, and the limit when these two operators collide. The leading operator that would appear in the operator product is sort of the lowest dimension operator in that representation. And from that, one can deduce that this conformal block, g delta L, should go like basically some power of z and z bar to the power of delta plus L over 2. And delta minus L over 2, it turns out. And for example, in a two-dimensional case, this g delta L can be simply expressed in terms of the hypergeometric function 2f1. I won't write the explicit expression, but some very explicit expression. Okay, so now the important property I would like to mention is that usually in at least in kind of old way of thinking about operator products or operator product expansion, the OPE in quantum field theory is you think of when the operators are kind of close to each other, can be replaced by some local operator. But one of the kind of the main insight that led to allow for progress in this bootstrap story is that in fact the OPE in a certain sense converges, and it converges everywhere. It converges in the sense that if you organize the expansion in terms of its conformal blocks, then this expansion actually converges on the entire complexity plane. There's a nice way to kind of think about that. So far I described this configuration which is general of the conformal transformation, where I have some R2 inside RD, and I put this operator at point 0, 1, infinity, and point z. You can map this by conformal transformation to a different configuration, where I think of this as the complex plane, and I put the 4 points at 1, minus 1, rho, and minus rho. So this lives on some small circle. This rho you can write as some r e to the I theta, where r is less than 1, like so. And there's explicitly, this is just z equals 4 rho over 1 plus rho squared. And in doing this way, you can map this entire complex z-plane to the unit disk for rho. So the rho now actually lives on the unit disk. So rho value less than 1. The statement then is that, for example, that you can rewrite the conformal block as expansion in rho, and you can talk about the convergence as power series of this in rho, and the statement is that this expansion converges on the entire rho disk. Now, we'll come back to this transition in a second. This power of conformal bootstrap comes from analyzing the crossing equation, which just says that you can do OP of 1 and 2, or you can do OP of 2 and 3. They're supposed to be equivalent. Now, if you only know about the convergence of OPE for two operators that are very close by, you may not be able to, you might think that in a regime where one OPE is valid, the other one may not be. So the whole point here is that, in fact, the convergence of OPE in this sense of conformal block expansion converges everywhere. So you can do OPE any order you want. You must get the same answer. And that in particular would imply that the crossing equation, which says that f of z bar should be equal to f of 1 minus z bar. This is equivalent to exchanging the operator phi 0 with operator phi 1. So instead of doing this OP of phi z with phi 0 first, you do OP of phi z with phi 1 first. Now this is quite non-trivial because if you plug into this formula, we find that well, I guess if you group this here, maybe I should just use a different name. We call this tilde. Then you have the equation that says sum of these positive coefficients, which is consequence of unitarity, multiplying this function g tilde at delta and L z minus this at g tilde at 1 minus z bar. This has to be equal to 0. But this this equation where it says that the sum, so these functions g tilde are universal, they're determined by the scaling dimensions. But these coefficients, while these are dependent on what theory you're talking about, they're a priori kind of the unknowns, as well as the actual possible delta values, which are expected to be some discrete set of values in the actual conformal field theory, are also a priori, let's say, unknown. But dependent on the property of this function, this kind of equation may or may not be possible to satisfy for positive coefficients a squared. I'll just give you a very trivial toy example to illustrate this phenomenon. So let's imagine that you can toy version. So let's imagine that this g tilde delta. Let's ignore the index. Let's drop the label L. Let me imagine that this is z to the delta. Now, of course, in actual theory, it's a much more complicated function. In fact, let me take this to be delta minus 2 delta phi because there was this 2 delta phi that I absorbed into that. So the kind of captures kind of the leading order behavior of this in a small dz bar limit. But let me pretend for the moment that this is the actual conformal block. Then you write this function f of z, which is sum of some positive coefficients over delta, z to the delta minus 2 delta phi. So the crossing equation, says that this must be also equal to sum over delta a delta squared, 1 minus z to the delta minus 2 delta phi. You can ask, is this possible? So a way to analyze this is to act on this equation with a linear functional in z. So let's say consider this operation alpha, which is linear functional, that is the derivative with respect to z evaluated at z equals a half. So that's z equals half is a point that's invariant under z equals to 1 minus z. So if you act on this, then you see that the crossing equation implies that sum over delta, a delta squared of alpha acting on this, which is equal to alpha acting on 1 minus z to the second power, must be equal to 0. And this, of course, you can all solve in your head. And it tells you that the sum of delta over delta 8 delta squared of delta minus 2 delta phi times 2 to the 2 delta phi minus delta equal to 0. Anyway, the point of this equation is that it says the sum of some positive coefficient times delta minus 2 delta phi is equal to 0. Now delta range over some discrete set of possible operator spectrum in your theory. For this equation to be possible, to possibly hold, generically delta can be arbitrarily large, so there has to be a delta that's smaller than 2 delta phi. So from this, you immediately deduce that there must exist some delta in the some, let's say, O delta that appears appears in this OPE of phi with phi, such that delta less than 2 delta phi. That's an implication of this quasi-equation. Well, you may not be very impressed by this quasi-equation because if you have a permission scalar operator, then OPE is expected to contain identity operator, and this identity operator has delta equal to 0, and if the delta phi is supposed to be positive in the unitary conformal field theory, so this equation, this constraint is trivially satisfied just because you have identity operator. But we don't have to stop there, because we can now consider a more general linear functional that is some combination, let's say A1 partial by partial z plus partial by partial z cubed. This whole thing evaluated at z equals 1/2. You see, if you do that, you still have an equation like this. But now, instead of this linear expression, you're going to have some cubic polynomial in delta. So alpha, acting on this z, delta minus 2 delta phi, if you plot it as a function of delta, it's going to, well, depending on the coefficient A1 is, which you get to choose. Could be some cubic polynomial like this. And if you choose this A1, you can choose A1 such that, so we already know that we have the identity operator sitting at delta equals 0. So if you choose this A1 appropriately, you can get your cubic polynomial to, let's say, just pass through this, like so, like that. Okay, so typically this is what alpha, this function acting on this quote unquote this toy conformal block is going to look like. Now it's slightly positive here, it will be positive here, and it's negative over here. This means that for the equation to be satisfied, you must have some operator sitting in this range. So if you call this intersection here delta star, you learn that there must exist some other operator O delta, which is not identity, that such that delta is less than delta star. Okay. Now, first to do the real conformal bootstrap, you have to replace this by the conformal block, and you want to consider not just a cubic linear functional, but linear functional of some hundreds, thousands of zeros to quarter, potentially. Then you get very, very non-trivial constraints. So there's this famous plot. I guess I won't really have time to discuss some of the Lorentzian properties of four-point functions, but that's okay. I just want to mention that some of you might have seen this this plot. So if you consider three-dimensional CFT, one of the remarkable success of this simple kind of idea of the analyzing class equation, if you assume, so if you assume that there's some scalar operator sigma of some dimension delta sigma, and you assume that in the OPE this thing contains identity operator and some other the first non-trivial scalar operator, epsilon, then you find that by an analysis that's similar to this, but slightly more elaborate, you find that given some value of, so here I'm plotting this linear functional, so this axis is delta. Now I'm plotting the bounds on delta epsilon given the value of delta sigma. So the delta sigma is the analog of this delta phi over here, so this is delta phi. So given the value of this delta phi, you do this crossing equation analysis using some, you scan over some space of linear functional, so you find some bound that says that this delta epsilon has to be less than some delta star. So this delta star would be somewhere over here. And if you change the value of delta sigma, then you find some other bound. You can kind of scan over all the possible bounds, and you kind of plot looks kind of like that. And there's this famous kink where you're supposed to find this kink corresponds to some delta sigma is like 0.518 something, and delta epsilon corresponds to 1.41 something, which is very close to the expected scaling dimension of the lowest scalar operators in the very famous 3D conformal field theory, which is the 3D critical IC-CFT. So that CFT is supposed to be the kind of Wilson-Fisher fixed point of the three-dimensional pi-4 theory, where you fine-tune the mass term. So this flows to some non-trivial CFT in IR, and the sigma is, roughly speaking, this pi field itself, and this epsilon is supposed to be pi squared, but they acquire some anomalous dimension, like so. But the really magical thing is that if you actually analyze, so this is from analyzing the four-point function of just phi, or in this case, sigma. But if you actually analyze the combined system of sigma and epsilon, with the understanding that there's a Z2 symmetry under which sigma is odd, the Z2 symmetry under which sigma is odd and epsilon is even, and if you analyze this kind of crossing equation on this combined system, it turns out, and also with the assumption that sigma and epsilon are the only relevant operator. So every other operator will have dimension greater than 3, or say greater than 3. Then it turns out that the analogous constraints up here, all this is in principle allowed, but the theory happens to sit at this kink over here. But the more general story, in this, if you analyze this combined system, then it turns out that under these assumptions, one finds this tiny little island of the allowed region and then some other disconnected region, and this IC CFT is sitting in this island, and this island is found to be very small, which seems to almost pin down the theory. I think I'm kind of out of time. I think I should wrap up. I don't really have the time to discuss, some open questions, but there are open questions everywhere. I started with 6 different approaches to quadratic non-perturbative linear quantum field theory, and focusing on one approach, and focusing on this very, very simple looking operator, which is a four-point function. But even from this, one can kind of uncover a tremendous amount of constraints. Kind of part of the goal of the conformal bootstrap program is to kind of explore the space of all possible conformal field theories, by looking for more and more solutions of these kind of constraints. Now coming from string theory, to me there's a kind of another important motivation for doing the bootstrap, which is that through the ADS-CFT correspondence, if you can learn about certain form functions, even say four-point function of some strongly coupled large and conformal field theory in certain regime, you can use it to recover the S matrix of quantum gravity, and by which I mean not just some kind of perturbed S matrix you can try to compute using some perturbed string amplitude, but the non-perturbative quantum gravity S matrix. There appears a hope of doing that, and so far the only kind of realistic way I can think of to approach that problem is actually by analyzing these ordered functions in some strongly coupled dual component. So I think I'll.
Suppose we have a 2D CFT with the orbital. So usually relevant operators from the twist sector. Can this approach to give more thing or can recap all the?
The orbital. Okay. So in fact, the general way to define the orbital CFT requires talking about the bootstrap. So I mean, what is the orbital? If you have a 2D CFT with some discrete global symmetry group G, you like to gauge the group G, but there may or may not be a unique way to do that. In fact, there may or may not be any consistent way to gauge G at all. So
assume we can engage.
Sorry.
Assume we can engage.
Yeah, but even assuming you can engage, there are different choices known as a discrete torsion. So in order to decide what to do, you basically have to. I mean, this is a long story, but roughly speaking, the story is the following. So you have some local operators, phi, the origin. You can act on this phi with your symmetry, which can be represented by the topological line operator. Now, the topological line operator can be cut open generally, because there's some correspond to some element G of the global symmetry group G. This line can be cut open and can end on some defect operator. And this defect operator is usually what we call the twisted sector states before the projection. So the whole point of this game is to understand, what is the space of defect operators and what are the current functions. But these are constrained by the similar kind of cross equation as what I described, but slightly more sophisticated because now you can talk about things like full-point function of not just local operators, but defect operators. They can have the lines connecting them. These are topological lines. So by this picture, I mean you have defect operators with actually topological line connecting them, and you can kind of move these lines into this other configuration. So there's some specific crossing rule. There can be some phases that intercept you to this kind of crossing operation, and these phases are what give rise to soft anomaly when anomaly is present. And then you can again talk about OP of the different operator by cutting this way or cutting that way, and that's the kind of general consistent condition what people needs to obey. So I mean it's all part of this story. Now in 2D, of course, in addition to this associativity of OPE, we also have the modular invariance towards one-point function, which then to define consistent 2D CFT, we have to have that additional set of consistent conditions as well.
So the main obstruction for non-CFTs is just the non-convergence of the OPE.
It's a little more than that. So in fact, as far as I know, there's no evidence that suggests OP does not converge. In fact, it's strongly suspected that the convergent OP work just as well in non-conformal theories. But it has been kind of difficult to prove that. So essentially, so we can, I can tell you more about my thoughts on this, but this actually was, I first
learned ask whether anything is known explicitly in any examples about the convergence of the OPE outside.
It's usually hard to write down explicit examples because we're talking about some kind of non-perturbative question about, you don't know so much about this. You can try to prove such a thing. The complication is that, as far as I understand, so the complication is the following. The complication is that you want to define the space of states on the sphere that surround these two operators. In conformal field theory, because of inversion symmetry, there's a Hilbert space of states on the sphere. But in general quantum field theory, there's no Hilbert space associated with the sphere because it's not a reflection invariant. So there's a space of states associated with the sphere with the outward orientation, and there's another space, there's field space with inward orientation. But they're not naturally isomorphic, and there's no natural inner product. There's a pairing, but there's not natural inner product on the space, so it's not quite a Hilbert space. And that prevents some analysis that's analogous to Richelieu theorem. So usually the way I like to think about OPE is that it's really in the same spirit of Richelieu theorem. Besides that, if you take the state produced by two operators inserted in this wall, it produces some states. Now you can try to produce the same states by operator in the vicinity of 1 point. Now you cannot produce exactly the same state because that state is a non-local operator to the operator. But you can get arbitrarily close to that. That's the operator product extension. So we'd like to prove something similar to Richelieu's theorem, but for this sphere in the non-conformal theory. But technically, that seems to be not so easy. As far as I know, this is not known to be a theory.
But I mean, I thought the intuition, just as you were saying, is that we can replace two operators that get very close to each other. We can approximate it by one local operator. And
Yeah,
the CFT, when things get far apart, it's the same as being close by inversion, so that you can never get too far away.
That's one way to think about it, but I don't really think that's the fundamental reason for the existence of the OPE. This way of Richelieu, like way of thinking about it, it strongly suggests that the OPE should exist and have infinite radius, or the infinite radius. Just as good convergent property in the general quantum field theory, but for technical reasons, it seems to be difficult to prove, and also we don't have good examples to check. But the real issue I would say is that the OP coefficient. So first of all, in a non-conformal theory, it's not clear how you want to organize the OP. The operator don't have definite scaling dimension, and the coefficients are not quite symmetric in the three operators. There isn't a straightforward quantity equation you can write down. Sure. Except for special cases where, for example, you imagine a situation with spontaneously broken conformal symmetry, then you might be able to do something. But other than that,
but let me ask you another way. If someone handed you, I mean, independent of how they got it, if someone just handed you a 4-point function for a CFT, say here it is. If they hand you the data of the 3-point functions, the operator content, and the 4-point function, you can check whether they're right or wrong, just to see whether it has the right OP in both channels. Do we have the analog of that check for any quantum field theory or not? I guess if you assume the OP is convergent, then we do have the analog of that check for any quantum field theory. Those 3-point functions would not be symmetric, so we'd have to define them. I mean, we'd have to define them as they show up in the OP. But you should see exactly the same 3-point functions in one channel and the other channel, and you can check if it's right or wrong, so long as it's convergent.
Yeah, I think you can check that, but I think that the issue is that you don't get as much power by analyzing a single 4-point function because there's not as much symmetry between these different coefficients. Now, of course, you can try to analyze all the n-point functions at the same time, but that's just going back to trying to ask for what is the most general solution to the Osterwalder-Schrader axioms, and that's a terribly difficult problem.
Okay, any other question?
Just trying to connect this back to the S-matrix bootstrap. So here it's key that you have two different expansions that are convergent in some overlapping region. But is the same true for the partial wave expansion in the S-matrix?
The partial wave expansion certainly in the physical regime has some nice convergent property. I mean. Right. Well, one has to be a little careful. So depending on where you can add a continuum to, sometimes this convergent property will fail. So one has to be careful. Right. But we expect that I think the partial wave expansion, at least on the first sheets, should be convergent.
In overlapping regions. So if you do the S channel expansion and the T channel expansion. Of course, each one in the right channel.
I think that, I think the overlapping regions very well. Yeah, I mean, I guess I didn't really say too much about that, but there's some formal analogy, but to me, well, I mean the technical approach to kind of to asymmetric bootstrap is a bit different. To me, the power of asymmetric bootstrap mostly have to do with the fact that you can kind of use your intent to bound the behavior near the cuts, and then you know something about authenticity, then you can say something globally on the complex aspect. So it has to do with knowing the analytic property on some domain. You know its boundary on some boundary of the domain, then you can basically kind of.
But that's for the S channel cut. But when you go to the U channel cut, then what happens?
Well, that's the hard part. So the hard part is precisely to control the T channel cut. So far, yeah, I mean, in some two-dimensional examples, this is relatively easy to understand because in that case, the T channel and S channel are directly related. So the T channel cut is also directly bounded by unitarity. So in that situation. So in the 2D version is like there's only one partial leg. In that case, things are easy, but the higher version is indeed more. But I should say that even in 2 dimensions, it's hard to write down a single set of consistent S matrix that has particle reduction from the end of it.
How much do we know the endpoint function of our extend operators like Y and surfaces? Is there some way we can approach this problem?
Well, you see, even the focal function of a single scalar operator is hardly ever known in a non-trivial quantum field theory. So when you're asking is much more difficult question. However, in principle, though, you see, in principle, if you know about these local operators, you should also be able to already, in principle, know about the things like line operators and so forth, because if you have a closed loop of a line operator, you can expand this on the basis of local operators. So in principle, local operators do know about this. How do you know this? Because, well, in principle, let's imagine you have some OP-like expression where we express this as a sum of a bunch of local operators. And then you take, you probe this with some other operator nearby, and study this current function, and you'll find that you can kind of bring this through, and you'll only encounter singularity when this other operator approaches this closed loop. If you really know the exact answer of this, say, Euclidean current function of this OP with some additional probe operator, then you can infer the fact that this is supposed to be describing a loop of some defect operator, some line defects. But of course, in practice, we can never write this out in any kind of controlled way. It's prohibitively difficult. But in principle, this local operator should know about this. Now, in practice, perhaps a more practical approach is to say that, for example, in conformal field theory, you can focus on the conformal defects. So you have some conformal line defect, and then you can talk about the local operators supported on this defect and ask, what are the possibilities? Your OP operates on the defect and OPs as the bulk operator approach the defect. You write down a set of crossing equations. Unfortunately, so far, this kind of equation that kind of mix the bulk operator and local operators on the defects do not have this kind of positivity property. So even in unitary theories, there's no kind of useful numerical approach, at least, to find constraints in the way I described over there. It's also similar to the kind of problem of finding possible boundary conditions. So even in 2D CFT, we understand a complete set of consistent conditions that a conformal boundary conditions should obey. So you can write down analogous set of crossing equations with things involving cylinder, Cohen function, and so forth. But it's quite hard to solve these conditions. And even in very simple examples of 2D CFT, outside the middle models, we don't actually have classification of boundary conditions.
Let's thank Xi again.